Okay, hey everyone. So today we're going to go through exam 1 from spring 2015. Just as a heads up, so I think if they keep the structure of the course the same, you wouldn't have, learned complex rotations yet. So problems 3 and 4 have some of that, and that would usually be on exam 2. But it's, I think the basic BKE stuff still applies here. So just keep in mind that this is a bit beyond what you would have for exam 1 if the structure is the same. So for the first problem, we have determine the dimensions of alpha, beta, and gamma in the absolute and gravitational system such that the following equation is homogeneous and correct. So, okay, so first of all, the absolute system, why is it? Okay, so the absolute system basically means that we can express our four fundamental quantities, which is mass, length, time, and then force. We express our force in terms of mass, length, and time. So that would be like F equals ma, so mass times length over t squared. And the gravitational system is where you express mass in terms of force, length, and time, where you have, then we have force times time squared over L length. So that's just what they mean by the absolute and gravitational system. So if we have like a force, we would express it all in terms of ML and T fundamentally. Okay, and then when it also talks about homogeneous, it's asking that that the dimension on the left-hand side equals the dimension on the right-hand side. Okay, and we're also given that F is a force, X is a displacement, G is a length, V is a velocity, and T is time, M is mass, and theta is an angle. So from that information, we can write down that the dimension of F is force. The dimension of X is a displacement, which is measured in length, so its dimension is length. Same thing with G, which is a length, so its dimension is length. And then for velocity, that's meters per second, right? So it's a length over a unit time. The dimension of T is time because it says so, and the dimension of M is going to be mass because it also says so. And then the dimension of theta, which is an angle, which we express in like radians, that is going to be dimensionless. So it would have a dimension of 1. Okay, so let's start with the left-hand side of the expression. So the dimension of the left-hand side equals the dimension of 0 to x of f over g dot squared dy. And this has to also equal the dimension of the second term, because how are you going to add two terms with different dimensions, right? You can't like add time, 5 seconds to 2 meters, right? So they have to be the same dimension if you're going to add them together, if this equation actually makes sense. So let's figure out what these dimensions are. So recall that an integral is really just a curve, say f of x, and it's the area under the curve for some distance x, let's say. So what you end up with is that the dimension of an integral from, let's say, 0 to x of f of x dx is just equal to the dimension of f of x times the dimension of x. So that's the kind of idea to keep in mind. It's just that the integral really is an area. So when you find a dimension, you're just taking the dimension of the integration bounds times the whatever is inside the integral, which in this case is f over g dot squared. So this then becomes the dimension of f over g dot squared times the dimension of y. So what is the dimension of y? Well, y is kind of like a dummy variable that you would put in place, and then you would actually evaluate the integral with these bounds. So really the dimension of y in this case is equal to the dimension of x. because at the end of the integration, you plug in x, and so that forms your actual, that's your, what forms your final result. So we have then that the dimension of y equals dimension of x in this case. And then we can do the exact same thing on this side where we have now a double integral, which you can really just think of as this first integration becoming that function f of x that you're going to integrate again over some integration bounds. So we look at the first, so we can like split this up into dimension of y, which in this case is going to be dimension of t, because again, as I said about the integration bounds, that's what you're actually evaluating at the end. Y is just a dummy variable. This, and then we times the dimension of 0 to x of f alpha v dx. And this just becomes the dimension of t times the dimension of x, which is the integration bounds, times the stuff inside the integral, which is this, times dimension of f alpha v. And this we can then rewrite. I feel like this is a little messy. So we can write this as, okay, let me just rewrite this for clarity. So dimension of f over g dot squared times dimension of x. Okay, so what is the dimension of f over g dot squared? Well, the dimension of f we have here is f. So I'm just going to keep it like that for now. And then the dimension of g dot is, so g dot is a time derivative of g, which is what the dot notation means. So that means if you imagine that, g has dimension L, so it's like a distance. Well, you can, or I think it's a length. Yeah, it's a length. But you can just imagine like if meters, you take the derivative of meters with respect to time, you just get like a velocity kind of quantity. So it would be meters per second. So the dimension of g dot is just going to be length per time. So length per time would be squared because it's g dot squared times the dimension of x, which is L, given here. And then we times that is equal to the dimension of t, which is time, times the dimension of x, which is length, times dimension of f alpha v. We know the dimension of f is going to be f, and then dimension of alpha we don't know. And then we have dimension of v, which is length per time, which is given right here. So now we can write this, simplify this as f t squared over L equals, let's see, this cancels, so f L squared dimension of alpha. And from this, we can just do algebra, and then we get that the dimension of alpha is equal to t squared over L to the 3. Okay, and I know that this problem asks for it in the absolute and gravitational system, but notice that we don't have any mass or force things here. So the way we did this, I guess, would be through the gravitational system, because we kept the F as is. So we have everything in the base units of F, L, and T. But even in the final result, there's no mass or force that shows up anywhere. So this answer is the same in the absolute and gravitational system. Alternatively, if you wanted to do this in the absolute system, you would have F equals ml over t squared. You can plug that into all these values of F here. And then when you simplify, you realize you get the same result, right? Because these F's will cancel. So in the end, if the absolute and gravitational system give the same result. So now let's go to the left-hand side, or the right-hand side. So we have dimension of the right-hand side equals dimension gamma over 2 times the dimension of m times the dimension of sine theta dot beta. Okay. The dimension of alpha or gamma over 2 is just going to be the dimension of gamma because 2 has no dimension, it's just a number. And then the dimension of m, we have that here is equal to m. So that's just going to be m times the dimension of sine theta dot beta. So sine is just equal to like the opposite divided by the hypotenuse, right? So that's a length divided by a length, which gives you just a dimension of 1. So the dimension of any trig function like sine, cosine, tangent, cotangent, whatever, that's always going to be equal to 1 because you're always dividing like the sides of a triangle by another side. So they have the same unit of length, so we get 1. But from this information, we know that also the angle, which is a dimensionless quantity, means that the dimension of theta dot beta is equal to 1. Because like radians are a unitless quantity. So, sorry, not unitless quantity. They don't have dimension. So it's just equal to, the angle is going to be equal to, is going to have dimension of 1. So this means that theta dot beta has to have dimension of 1 as well. So we know that dimension of beta equals 1 over the dimension of theta dot then, just from algebra. Now we know the dimension of theta is equal to 1, so the time derivative of that is just going to be equal to the dimension of theta divided by the dimension of time, which is like the time derivative, right? So this means that the dimension of theta dot equals 1 over time. So that means 1 over the dimension of theta dot is time. So dimension of beta is equal to this. So that is what gives us beta. Again, it's the same in the gravitational and absolute system because there's no mass or force involved. The expressions will be the same. And then also we need to find gamma. So great, now that we have our two sides of the expression, so we know that, so we know that the dimension of, so what happened? Anyways, so we know the dimension of the left-hand side is equal to, so it's equal to force times, I'm going to get rid of these slashes so we can be clear about what it actually is. So we found the dimension of the left-hand side is equal to ft squared over L, which is also equal to fL squared times the dimension of alpha. And now we also know that the dimension of the right-hand side is equal to the dimension of gamma times the mass, because the 1 doesn't do anything. So what you do now is you can set these two equal. So we can say that ft squared over L equals dimension of gamma times m equals, I should write this. So equals a dimension, equals fL squared dimension of alpha equals dimension of gamma times m. Okay, well, we already found dimension of alpha, and honestly, this is just like, honestly not that useful because we already know what the right-hand side and left-hand side should equal. So we have f times t squared over L is equal to, so this is going to be the dimension of the left-hand side, and then is equal to m times dimension of gamma, which is the dimension of the right-hand side. So this means that f t squared over L m equals dimension of gamma. Okay, so like let's evaluate this in the gravitational system. So in the gravitational system, we write our mass in terms of force t squared over L. So m equals ft squared over L, so ft squared over L times ft squared over L just gives us 1. And then we can similarly do this in the absolute system. So in that case, we write force in terms of mass, length, and time. So we get ml t squared times t squared over lm everything cancels and just we end up with 1. So clearly the dimension of gamma is equal to 1. And it's the same in the absolute and gravitational system. So those are our answers for problem 1. Okay, in problem 2, we have the length of a vector v is 5. The length in the E3 direction is 3. Find the components of v in the E1, E2, E3 hat direction, and the dot product and cross product of v with this other vector w. Okay, this is the vector v, and this is, I'm guessing, a v. It just doesn't look quite like it from this angle. So v points from here to here, or from here to here, and then we know that it's this distance 3 in this direction, and that this vector has length 5. So what that means is that the magnitude of v is equal to 5. Find the components of v in the E1, E2, E3 hat direction. Okay, so first thing we can do is like consider this triangle here. So this is going down, so this is at a right angle. So if you can like try to visualize that, because it's basically taking this like projection of a vector and then just like grouping it downwards. And so the resulting like triangle that we get, that we're looking at here, this is at a right angle. So I can draw that now as this, right? This is, this distance is 3. And then we know this distance is 5. So just from Pythagorean theorem, this distance, which I'll call d, so d, d is equal to 25, so 5 squared minus 9, right? So 5 squared minus 3 squared, square rooted, is equal to 4. So now we get that, which is cool, but we need to find the components in the E1, E2 hat direction. But we can do that because we know now that we have the angle of this d projection vector onto the E1, E2 hat plane, and the magnitude. So we can draw this triangle now. And when we draw that on the E1, E2 hat plane, it looks like this. So this angle is 60 degrees. This length, which is d, is equal to 4. So from cosine-sine relations, we can write that in the E1 hat direction, this is equal to d sine 60 degrees, and then this is equal to d cosine 60 degrees. Yeah. So that's just 4 cosine 60, and then 4 sine 60. So let's let's just like look at the problem then. So we know that the component in the E3 hat direction is already given to us in the problem, which is 3. So in the E3 hat direction, we have 3 units downwards. So right, the vector points down, so it would be in the negative 3 E3 hat direction. So let me just rewrite that as this. And then now we have the E1 hat component, which from this vector, it points this way. That means it's equal to, we found that here, 4 sine 60. So sine of 60 is square root 3 over 2. I'm just going to write that later. And then it also, so we had the E1 hat, now we need the E2 hat, which we found here to be 4 cosine 60. E2 hat. And that's our expression for v, right? It makes sense because the vector really is just, if you go this way, then you go this way, and then you go down. So all we've done is decompose it into those vectors. So now we can just rewrite this as 2 square root 3, because sine 60 is root 3 over 2 E1 hat. Plus, and then this is 4 times 1/2. So that's just 2 E2 hat minus 3 e3 hat. So the components in the e1 direction is 2 square root 3. Component in the e2 is 2, and then in the e3 is negative 3. So this is our final result for part 1. Now we can do part B, which is the dot product and cross product with V with W. So now it's asking for V dot W, which is a dot product. So we can write this as 2 square root 3 e1 hat plus 2 e2 hat minus 3 e3 hat, dotted with 5 e1 hat minus 2 e2 hat plus 1 e3 hat. And remember, with dot product, all you do is you take the components of the vectors with the same vectors. So I do e1 dot e1. This gives me 2 square root 3 times 5. And I do the same thing with e2. So that's 2 times negative 2. And the same thing with the e3. And then I multiply that together to get this. Because a dot product of anything of like 2 orthogonal vectors, which is the case for e1, e2, e3, is equal to 0. And it's only ever equal to 1 if it's the same vector dotted with itself. So that's why we only just care about the vectors with the same, with the components of the same unit vector, because all the unit vectors are orthogonal. So this gives us 10 square root 3 minus 4 minus 3, which just becomes minus 7. And that's the dot product. V cross W, which is, okay, so I guess there are 2 ways to think about this. So the first way, we can do like what we originally just wrote out, like in the dot product. So we do cross 5 e1 hat minus 2 e2 hat plus 1 e3 hat. There are 2 ways to go about this depending on which one you prefer. So one is you can just remember how the orientation goes. So if you're going 1, 2, 3, so you go, if you have e1, for example, cross e2, you get a positive e3. If you do e2 cross e3, you get a positive e1. And then if you do e3 cross e1, you get a positive e2. And then if you go the opposite direction, it's negative. So that's one way to do it. The other way is to do the determinant method, which would mean you take the vectors. So we have the unit vectors e1, e2, e3. And then you put the first unit vector in this first row, and then the second unit vector in the second row, and you do the determinant. So if you haven't learned determinants yet, all you do is you take, I'll just do the determinant method. Actually, I'll just like briefly go through both, actually. Okay, yeah. So the determinant method, you first X out the first column, so that's the e1 hat column, so I have e1 hat. And then I take the determinant of this, which is just equal to this product minus this product. So that means I have 2 times 1 minus negative 2 times negative 3, which is 2 minus 6, which is negative 4. That's the first column. Then I X out the second column, but because the second column, it's special, so you have to put a minus sign in front. So minus e2 hat, and then I do the determinant of the remaining these terms, so 2 times square root 3 times 1, minus 5 times negative 3, which is just 2 square root 3 plus 15. And then finally I do the exact same thing with the last column. This one is no special stuff going on, so you just have e3 hat times the determinant of this, which is just 2 square root 3 times negative 2 minus 5 times 2. So yeah, that gives me negative 4 square root 3 minus 10. Okay, and then we can just clean this up a bit and then do negative 4 e1 hat minus 2 square root 3 plus 15 e2 hat minus 4 square root 3 plus 10 e3 hat. I should have done this to denote that it's a vector. So this is the cross product. And if you were to do the 1, 2, this method, you would just notice that E1 cross E1 is going to be 0. E1 cross E2 gives you a component in the E3 direction. E1, E3 gives you a negative in the E2 hat direction. And then you just continue this distributive process onwards. Notice that if you have like an E1 cross E1, that gives you a 0, because the definition of a cross product is like the terms that are, it's the vector that is like orthogonal to both of the initial vectors. So the reason that like obviously E1 cross E1 is equal to 0 is just because like the definition of a cross product is like geometrically speaking, is like the vector that's perpendicular to both of those vectors, and like the magnitude of this cross product vector is equal to the area of the parallelogram that your two composing vectors produce. But if you have like the same vector, there's no area, so your cross product is going to be equal to 0. So that's why the E1 cross E1, E2 cross E2, E3 cross E3 is equal to 0. Yeah, so that was the second problem. That was pretty nice. Okay, hi everyone. So this is my second time recording this problem because I can't do cross products and ended up making negative errors, which I think was a bit too confusing to go back on. So I'm just gonna redo it, and sorry if my voice sounds dead because talking through this problem was a lot. And it's kind of long, but it's not a bad way. It's only a bad way if you had to do it 2 times in a row. So anyways, in this problem we have a ship Adria which sails at constant velocity v in the E2 hat direction. On the front of the ship, the Poseidon fork, which is this thing here, is rotating at angular velocity omega around the vertical axis, so it's drawn as rotating around this way. At 1/2 of the fork at a distance r from the center, so this is the center, a distance r this way, a rope of length L is holding not a sailor Tom rolled up in a point P at an angle phi to the fork. To shorten his punishment, Tom, this thing right here, continuously tries to pull himself up the rope, so he tries to keep going this way and aboard again. We want to find nice expressions for Tom's angular velocity, the angular velocity of P with respect to the E frame, which is drawn here, and angular acceleration of alpha, so that alpha of P with respect to the E frame. So this is relative to the C frame, which is the E frame. And we also want to find expressions for his velocity and acceleration relative to the ground frame when phi is 90 degrees. So that's a key point here to note. So we have E2 hat, E3 hat pointing up this way, and then E1 hat coming out of the page. So the first step in all of these cases is you want to create your reference frame. So the first rule of thumb is to generally you create a reference frame for all the different complex rotations. So in this case, we have one complex rotation of the fork, which is going around here at angular velocity omega. And we also have Tom, who is swinging back and forth and taking the L, kind of like I am right now after doing this problem another time, at an angle phi from horizontal. So I'm going to denote phi as being counterclockwise, so going counterclockwise up from this vertical here. And this would mean that he is rotating at angular velocity of phi dot, since that's the change in velocity of the change in angle with respect to time. So that's the angular velocity of Tom swinging back and forth here. Okay, so then I want to create my 2 reference frames because these are complex rotations. So because Tom is attached to the fork and the fork is rotating with respect to the ground frame, I want to create 2 frames, one for the omega rotation of the fork and one for the rotation / swing of Tom. So I'm going to create my first frame here in the fork. So I'm going to call, let's see, this, what should I call this? I'm going to call this direction A2 hat and this direction A1 hat. I should draw this clear. It's going to get messy. So in this direction is A2 hat, in this direction is A1 hat, And then, it's going to be an A3 hat coming out of the page, but like in this very instant. But obviously A1, so A1 and A3 are like rotating about A2, right? If it's like this, the fork is, wait, I can't draw. Okay, the fork looks something like this. And this fork is spinning around, it is spinning around the A2 hat axis. So A3 hat may not be pointing out of the page all the time because it's spinning around A2, but just know that in this instant that we've drawn, it seems as if it's going to be coming out of the page. Okay, and then I'm going to add another frame, which is the B frame. So I'm going to add that pointing from here to Tom. So how do I draw this? So I'm going to have the B1 hat, let's call this the B1 hat going this way, B2 hat going this way, and then B3 hat will again, like A3 hat, come out of the page. So notice that B3 hat and A3 hat will point in the same direction. Okay, so I am going to first do part A. So part A is asking for what is the angular velocity of Tom with respect to the ground frame. So again, this is a complex rotation. So what does that mean? You can write the complex rotation of Tom in terms of the individual complex rotations. So in this case, Tom is rotating with respect to, so Tom is in the B frame, so I'm going to call this the B frame. The B frame is rotating with respect to the A frame, right? Because Tom is swinging back and forth here, like this way. So this means that there's an angular velocity of the B frame with respect to the A frame. And then, not only that, the A frame is rotating with respect to the ground frame. So the A frame is rotating with respect to the E frame. So this means that I can sum these complex rotations together and get the angular velocity of Tom with respect to the E frame. So what's the angular velocity of the B frame with respect to the A frame? Well, we do the right hand rule, so we curl our right hand, our second, third, fourth, fifth fingers in the direction of Tom's rotation. So I defined earlier that Tom is kind of going this way. So I defined phi as relative to the vertical in the counterclockwise direction. So this means that his angular velocity is going to be phi dot, curling our fingers in the direction of the rotation, and our thumb should be pointing out of the page in the B3 hat direction. So the thumb points in the direction of the angular velocity. So we have the angular velocity of the B frame with respect to the A frame is going to be phi dot B3 hat. And we can do the same thing with the fork. So curling our fingers in the direction of omega, your thumb should be pointing down. So it should be pointing this way, which is in the opposite direction of A2 hat. So it's going to be minus capital omega A2 hat. Okay, so this is our angular velocity, but I'm going to write this in a different, all in terms of the A frame, because it's going to make our lives in the next step a bit easier. So I'm going to try to write everything in terms of the A frame. How can I convert B3 hat into the A frame? Well, we just observed that the A3 hat vector points in the same direction as the B3 hat vector, right, based on the way we defined our frames. So I can write phi dot A3 hat minus omega A2 hat. And this is going to be equal to the angular velocity of Tom with respect to the E frame. Okay, now we have to find an expression for the angular acceleration of Tom with respect to the ground frame. So this is then not going to be equal to the angular acceleration of B and A plus the angular acceleration of A and E. This is not true. Instead, this is going to be equal to, let's just remove this because it's not correct. You have to do the BKE and take the time derivative of the angular velocity with respect to the E frame. So I'm going to do that now. This basically means I need to take the time derivative of phi dot a3 hat plus, nope, not plus, minus omega a2 hat with respect to the E frame. So this is why I originally wanted to write this all in terms of the A frame, because if I wrote in terms of the B frame, I would have to split up each of these components when I do the cross product, or sorry, when I take the BKE. And that just like makes my life complicated, because then I have to start incorporating the omega B and E term when I do the cross product, and just splitting it up makes it much more complicated. And the A frame is also extremely close to the E frame, right, compared to the B frame. Like the angular velocity of the B frame with respect to the E frame is this whole thing. But the angular velocity of the A frame with respect to the E frame is just one term. So this will also make my life easier when I do the BKE. So this is why you probably want to kind of make your life easier and write everything in terms of one frame, as is shown here. So this becomes applying BKE, taking first the time derivative of the original vector with respect to the frame it's already written in, which is the A frame, plus the angular velocity of that frame with respect to the E frame, crossed with the original vector, which is phi dot a3 hat minus omega a2 hat. Okay, this just becomes phi double dot a3 hat minus omega dot a2 hat plus the angular velocity of A and E we found to be this from the previous part. So it's negative omega a2 hat cross with phi dot a3 hat minus omega a2 hat. And I think it doesn't say anything about things being constant. So it only says that v is constant, so v dot is equal to 0. But for this, it doesn't say anything about being constant, and yeah, it doesn't say this is anything constant either. So we cannot assume that anything equals 0, so we just like keep these terms here. Okay, so then I can write this as phi double dot a3 hat minus omega dot a2 hat plus, okay, cross product time, so omega phi dot, so a2 cross a3 is going to be a1, but there's a negative, so there's a negative sign here. And then a2 cross a2 is just going to be 0, so we leave it as is. Okay, so that should give you the angular acceleration. Let me just check my work. Unlike what I did last time. Yeah, so this is correct. This is the angular acceleration of Tom with respect to the E frame. Okay. Okay, so now we want to do part B, which is where things get really entertaining. We want to find the velocity of Tom with respect to, oh my goodness, I don't know what that was. Okay, anyways, so we want to find nice expressions for Tom's velocity and acceleration. So let's just start with velocity because it's a doozy. So first of all, how do we find the velocity? So this is exam 1, so technically you haven't really learned velocity expansion or acceleration expansion yet, so I'm going to do things the BKE way. But if you have, you can like try your hand at this, and I can make another video doing this the BK or the velocity expansion and acceleration expansion method if people want. But for this case, I'm just going to do the BKE. So the way we do this with BKE is we know that velocity is a time derivative of position. So we have some position vector, and we choose some point O that is fixed in the E frame because we want to find the time derivative with respect to the E frame because we want the velocity with respect to the E frame. So we pick some point O that is fixed in the E frame, and then we draw that to our point of interest, which is in this case Tom, point P. And okay, yeah, so we need to find our point O. So there's a few things. So we want to pick a point O that is fixed, and we know that the ship is moving, and we know that this is spinning, and then that Tom is also spinning. So I'm going to pick the point. What should I pick? I think I'm going to pick this. Oh. Okay, I'm going to pick. Wait, sorry. Oh no. Okay, hold on. Okay, I'm going to pick. What am I doing? Okay, I'm going to pick this point here. So this is point O. And then I'm going to define a point that I'm going to call point A here. And point O and A are in a line. So it's like this, right? And I'm just going to ignore the distance between them for now. And then, oh, why is that? Okay, I want this to be like more up. So I'm going to do this. So it's like here. So like this point, okay, this is really, so this point, which I'm going to call B, is going to be parallel, like in a line with point A, which is here, and point O, which is like over here. Okay, hopefully that is kind of clear. Point A is like in the middle of the fork, and then point B is at the edge of the fork where it's attached to the rope. And then point O is just some point floating in midair here that is fixed. Okay, so the position vector from O to P is then also, as a side note, point O is just a random point that I've picked that's fixed. You can pick any point, here or here. It's just, it would be a little more complicated because you would have to have this point go up, then over and down. And so this thing right here, you don't actually know how high that is. So you would want to choose a point that is easy to find the distances for, which I'll show in a minute why that point is easy. So what is ROP? ROP is equal to, first, some distance from O to A, and then we go from A to B, and then B to P. So I'm going to call the distance O to A just going to be like L. And then A to B, we know is going to be a distance R along the, oh, that got erased too. Oh, wait, no, it didn't. It's down here. So A1 is along this direction. It's fixed in the fork. So we go distance R along the A1 hat direction. And then we go from point B to point P, which means we go distance L, little l, along the B1 hat direction. I'm actually going to call this like X or something, so it's easier. So let's just write that down. So it's going to be X in this E2 hat direction, right? Because the ship is going at constant velocity V in the E2 hat direction. Plus distance R along the A1 hat direction. And then distance L along the B1 hat direction. Okay, now we're like, okay, but what is X? Well, it says that the ship is going with constant velocity in the E2 hat direction. So this means that X is just equal to velocity times time, right? So I'm going to replace this X with VT. Okay, now when I look at this velocity expression, I'm going to write it now in terms of each individual component. So we've established what ROP is. And hopefully you see why I now picked O, because it's just much easier to only have to define this horizontal distance, because it just automatically equals VT. If we added some horizontal distance, it would kind of like carry through the entire process of the BKE and would be very difficult. So it's just easier to select the point O to be there. Okay. I'm now going to, so we know what ROP is, and now I apply the BKE. I'm going to split it up into its individual components because all of these terms are written in different reference frames, right? One's written in terms of the E, one's written in terms of the A, and the other one is written in terms of the B. Okay, this one, first term, then should be, oh my gosh, okay. This first term should be pretty easy because it's just equal to V E2 hat, right? It's already written in the E frame, so it's pretty easy to just take the derivative. Okay. Okay, so the next one is the R A1 hat term. So I'm going to just write this in this color. So this becomes R dot A1 hat, right? We apply BKE. We first take the time derivative in the frame it's written in, which is the A frame, plus the angular velocity of the A frame with respect to the E frame, crossed with the original vector. Great. And then, oh my gosh, okay. So, and then we have the second term, which is the B frame term, which is just equal to the time derivative of it with respect to the frame it's in, plus the angular velocity of the frame it's in, written in with respect to the E frame, crossed with the original vector. Okay, so this becomes V E2 hat plus R dot A1 hat, and then recall that omega A with respect to the E frame is equal to, from here, it's negative omega A2 hat. Cross with RA1 hat plus L dot B1 hat plus, so now we have the angular velocity of the B frame with respect to the E frame. That is equal to the angular velocity of P with respect to E, because if you recall, when we write this, we are basically saying that this is the angular velocity of the B frame with respect to the E frame. So we can write this as phi dot A3 hat minus omega A2 hat crossed with LB1 hat. Okay, so first, a few simplifications we can make. So we know that R dot, which is the distance between the middle of the fork to the edge of the fork, so this distance here. So this distance here. We know that it's going to be constant because the fork is not like expanding or contracting and doing crazy stuff. It's not mentioned in the problem at least, so I think we can assume that that distance is not changing. So I'm going to just have R dot is going to be equal to 0 because that distance is fixed. Okay, well that's pretty much it. So we can just do V E2 hat plus, so omega cross R is equal to omega R A3 hat, and it should be correct. So if this is A1, A2, A3, 0, 0, 0 minus this. Oh yeah, so this is correct. So I'm just checking with the determinant method. I do go over this in some other video, but it's okay. We can go over this more in depth when we do this fun cross product. We can review that again. So now we get plus L dot B1 hat plus, and this is where things get fun because we're like, oh no, these are in A frame coordinates or in unit vectors. How can we cross this with a B vector? Well, we get to do our fun vector projection now because we need to convert everything into the same frame. So I'm just going to convert the B unit vector into the A unit vector because it just is easier than converting two A unit vectors into a B unit vector. So I'm like, how do I write this in terms of A frame unit vectors? Okay, so this requires us to go up to our beautiful drawing. So vector projection just means that you're like looking at something from a certain angle and you put these vectors, unit vectors that you've drawn on top of each other. So in this case, let's just say I'm like looking at this face on, right, as I currently am doing. So A1 points this way, A2 points this way, and then A3 points out of the page. When I look at that, I can then write this. Okay, And then I look at the b unit vector, and then I'm like, okay, so if I'm also looking at it from this face down angle, I am then going to see b1 going this way, b2 going this way, and then b3 is in the same direction as a3 hat, as we discussed before. And we also should draw some geometry of the problem. So we know that from this part here that this b1 hat always points towards Tom, right? So it's going to be at an angle phi from the vertical. So this is like the vector projection ideal. You just like look at it from a certain perspective. In this case, we look at it from top down, and then we draw what the A frame and the B frame look like on top of each other, and then we can write things in terms of each other. So in this case, I want to write my b1 hat vector in terms of the A frame vectors, right? Yes. So, okay. So how do I do that? Well, I just like draw some geometry. So we know that this angle is phi. This means that this angle is 90 minus phi, but that means this angle is then phi as well, because the b1 and b2 hat are orthogonal to each other, right? Right, a1 and a2 are also orthogonal. So b1 hat is then equal to, we just do some trig, and I think sometimes it helps if, oh, actually in this case I think it's fine. But sometimes if you want to like write the A frame vectors in terms of the B frame vectors, it helps to like tilt it like this, and then make the b1 and then b2 hat, in the typical orthogonal direction, and then just like redraw the a1 hat or a2 hat in this direction. So that's another way you can go about this, but it's just up to you and what you prefer. In this case, I think it's, I'm just going to do it this way. So the b1 hat goes this way. We can use trig, so cosine of phi is in this direction. So that's opposite the a2 hat direction. So we have negative cosine phi a2 hat plus sine phi a1 hat, right? And go this way, right? So, yeah, that's our vector projection. Now we can put that into the bottom thing here. So we have this becoming b1 hat equals negative cosine phi plus sine phi a1 hat. Okay. And then we just plug that in. So I'm going to write this out. Okay. And then I'm going to do the determinant method here. So I'm just going to write this. I'm going to add this L in. So L is equal to negative L cosine phi plus L sine phi a1 hat. Okay. And then I'm going to do the determinant method now because this is a little too advanced for my small brain. So first I'm going to put the unit vectors up here. Okay, actually, maybe I should write this out just for clarity. So it's going to be phi dot a3 hat minus omega a2 hat cross with negative L cosine phi. Oh, let's move this over here. A2 hat plus L sine phi A1 hat. Okay, so I'm going to use a determinant method for this because I don't trust myself anymore. This becomes, I plug in the first term, which is this, into the first row. So this gives me 0, negative omega phi dot. And then I plug in this term into the second row. So this is L sine phi. And then negative L cosine phi 0. And then I do a determinant, which means I take the first column, I get rid of it, and this means the coefficient is the determinant of this expression here, which is going to be 0 times negative omega minus negative L cosine phi times phi dot. So this gives me L phi dot cosine phi. Great. Then I move on to the next one. Because it's the middle one, I put a minus sign in front. So minus A2 hat. And that's a determinant of this little matrix here. So this becomes 0 times 0 minus L sine phi times phi dot. So that is 0 minus that, which is equal to negative L phi dot sine phi. And then I do the same thing with the last column, A3 hat, and I take the determinant of this. So the last column is normal, so you just do plus A3 hat, and then we have 0 times negative L cosine phi minus L sine phi times negative omega. So this gives you 0 minus that, which is just L omega sine phi. Great. Yeah, and so then we can just put this as V E2 hat plus omega R A3 hat plus L dot B1 hat plus L phi dot cosine phi A1 hat minus, or plus, because these cancel, plus L phi dot sine phi A2 hat plus L omega sine phi A3 hat. And then I can like combine terms now, so I'm just gonna move this term over here. I can just move all these over. This becomes omega R plus L sine phi A3 hat. I just combined terms there. Whoa. Okay. And that is going to be our expression for the velocity of point P with respect to E. So let me just look real quick. Okay, yeah. And then you're like, oh, what an interesting term here. This is correct, by the way, but this is such an interesting term. Wow. Why does it look like the coefficients are the same, but it's just a difference between a cosine and a sine? Well, you can actually rewrite this in a cleaner way if you look at the geometry again. So notice that this term is just equal to L phi dot times cosine phi A1 hat plus sine phi A2 hat. Okay, and then I'm like, oh, let's look at our beautiful vector projection. So we have cosine. So let's look at the B2 hat unit vector. How do we write that in terms of the A unit vectors? Well, that is equal to cosine phi A1 hat plus sine phi A2 hat. And I'm like, what? That is the exact same expression here. So I can just write it as L phi dot B2 hat. And this is quite nice because it just makes our expression look nicer. So then our final expression is VE2 hat plus L dot B1 hat plus L phi dot B2 hat plus omega R plus L sine phi A3 hat. And then, yeah. And then we're like, this is our final expression, but it is actually not, because this is asking us for the velocity when phi is equal to 90 degrees. So we plug in phi equals 90. And this gives us V A2 hat plus L dot B1 hat plus L phi dot B2 hat plus omega R, and then omega R plus L, because sine of 90 degrees is just 1. So our final expression when phi is 90 degrees is this. Okay. Now we go on to the next part, which is the acceleration. So I'm going to move this even more far down. Okay. So to find the acceleration, we just really have to do BKE again. It is the harsh reality of life. So we just need to do the time derivative of the velocity of p with respect to e with respect to the e frame. Now, we do not take the time derivative of this. This is incorrect. We take the time derivative of this expression because it doesn't make sense, like if you're taking a time derivative, to take the time derivative at a single point. You always take the time derivative of the general expression, and then afterwards you plug in the condition it is at, right? So I feel like a good analogy for this is like what's a good analogy? Like if you throw a ball at VT and then, you're throwing a ball and your position is like VT. And then at time like t equals 1, your ball has traveled like 1 feet. So your position vector is just, let's say 1 meter. And then you're like, what's the velocity? And then you just take the time derivative of that. And then it's obviously equal to 0. If it's at a specific point, there's no way the velocity there is equal to 0 because the actual velocity is equal to v, right? Like dx dt equals v. So that's why it doesn't make sense to take the time derivative at a specific moment. You have to take the time derivative of the general expression first and then plug in the values. So anyways, just a random thought. Okay, back to this problem. So we do this expression and plug that in here. And we get v dot, okay, I'm going to split this up again. So I split up the terms because they're all in terms of different coordinate systems, right? So I first did the time derivative of v2 hat, and then the time derivative of L dot and then the A frame. Yes, I think that's right. Okay, so this becomes obviously just v dot e2 hat because it's already in the e frame, so we just take the time derivative like we normally do. Now, in the problem statement, it said that it's constant velocity, so v dot is equal to 0. So we can just say, boom, 0. And then I'm not going to write this out, so I'm going to put this as 1. Ooh, I should color code it. 1 plus 2. So we can do these separately and not suffer trying to put them on the same line. Okay, so in part 1, BKE time. So this, using the BKE, becomes first the time derivative of L dot B1 hat plus L phi dot B2 hat with respect to the frame it's already written in, which is the B frame. So this just becomes L double dot B1 hat plus product rule L phi dot phi double dot plus L dot phi dot B2 hat. And then wait, what am I doing? Oh yeah, okay. So this is the time derivative of the original vector with respect to the B frame, plus the angular velocity of the B frame with respect to the E frame, crossed with the original vector, L dot B1 hat, plus L phi dot B2 hat. Okay. And then we set that equal to, so that becomes this. Plus the angular velocity of B, which we previously found was up here. So this is phi dot A3 hat minus omega A2 hat. Okay, notice how I wrote phi dot B3 hat, and I remember this is a valid expression as well, like this is what we had up here. I'm doing that now because I kind of don't want to convert these two terms into the A-frame because it's just more complicated, so now I've decided to just do it in terms of the B-frame. And like you could do it either way, but personally I think it's easiest because we know A3 hat equals B3 hat, so that's like the easiest conversion we have. So now it's just a matter of converting this A frame unit vector into B frame stuff. So A2 hat. Let's go up here and look again. So A2 hat, right? And now like I personally think it's useful to look at this picture now. So we know that phi is going from, so we've like shifted it this way, so now phi goes like this, and then this is phi. I think you have to stare at it for a second just to see, because all we've done is like rotate this picture like this way a little. But yeah, so we can write A2 hat now in terms of this. So A2 hat is equal to, I'm going to draw another line too because it helps me. So I'm going to extend B1 hat this way. Oh my gosh, no. Okay, I'll extend B2 hat this way. And then this is 90 degrees, right? And then I'm going to be like, oh wow, this is also phi then, because, right, 90 degree angles, this is 90 minus phi, so this becomes phi. Okay, now we can write A2 hat as going along this way. That's equal to negative cosine phi B1 hat, because it's going in the opposite direction of the B unit vector. Then we also go up sine phi, so plus sine phi B2 hat. Yes, yeah. So hopefully you see how that happened. We just, tilted our vector projection a bit, and then we wrote A2 has a vector going this way plus a vector going this way. And now we can put that back down here, so that's negative cosine phi B1 hat. Yep. Okay. And then we can evaluate this glorious cross product. So, okay. How do we even do this? Okay, so I'm just gonna write this over here. So this becomes phi dot B3 hat minus omega times negative cosine phi B1 hat plus sine phi B2 hat crossed with, so this entire term crossed with L dot B1 hat plus L phi dot B2 hat. Okay, so this cross product we can write in determinant form as B1 hat, B2 hat, B3 hat. I put the first term in the first row, so phi dot, and then omega cosine phi, and then negative omega sine phi, and then L dot, and then the second term now goes in the second row, and it's this. Okay, so now here I'm going to make the simplification because it makes the problem much easier. So we're not like taking the derivative after this anymore, so I think it's okay if we just plug in the phi equals 90 degrees. And we just start doing the calculations that way because we don't take a derivative of anything in this expression, right? So it's okay for us to plug in the value at that instant. So cosine of 90 degrees is just 0, so this becomes 0. Sine of phi is just 1, so this is just 1. So then our cross product becomes, 0, negative omega phi dot, 0, L phi dot, and then L dot. We plugged in phi equals 90. Okay, and this actually makes life much better. So we have, first we take the B1 hat column, B1 hat, and then we have 0 minus L phi dot times phi dot, which just means it's phi dot squared. This is a negative. Second one, we take a minus because it's always the middle one that has a minus, so minus B2 hat. And then we take the determinant of 0 phi dot L dot 0. So 0 times 0 minus L dot times phi dot, which is just plus, we do the same thing with the third column. And then we have 0 times L phi dot minus L dot times negative omega. So that's just positive L dot omega. Okay. So now we can just write in this as, just copy this. Technology is crazy. This is okay. And plus negative L phi dot squared B1 hat minus or plus L dot phi dot B2 hat plus L dot omega B3 hat. And we can combine terms, so this gives us L double dot minus L phi dot squared B1 hat plus 2 L dot phi dot plus L phi double dot B2 hat plus L dot omega B3 hat. So that's our first term. And then our second term, okay, actually, let me just check the first term first before we move on and forget this negative sign, potential error. Okay, great. Yes, it works. Okay, so now for part 2, we have the time derivative of this term. So first of all, we take the time derivative with respect to the frame it's written in, which is the A frame, of this whole mess. So omega r plus omega L sine phi. This A3 hat. Plus the angular velocity of the A frame with the E frame, crossed with omega r plus, so this is the original vector, yeah, yes. Okay, no, we cannot plug in phi equals 90 degrees here because we still have to take the derivative. But we can do it here because we're just taking cross products, which doesn't actually have any derivatives in it, obviously. So we can't plug in phi equals 90 degrees here. But anyways, so first we take the time derivative of this, which just becomes phi dot r. Remember, r is a constant because the fork is not like expanding or contracting. So the distance stays constant. Plus, here we need to do like a 3-way triple. Wait, what product? Wait. how do you do these again? Okay, I think you do this. So you do omega dot times this, right? Oh, what am I? Okay, yeah. So this plus, then you do the time derivative of L sine phi, which is L dot sine phi plus L cosine phi times phi dot. Because you have to do like the product rule for all three of these because they are all changing with respect to time. Then this becomes a 3 hat plus the angular velocity of A and E we found was negative omega A2 hat crossed with this term, so omega r plus omega L sine phi A3 hat. So because it's a cross product, we can already just immediately plug in, phi equals 90 degrees. So this becomes 1 because sine of 90 degrees is just 1. And then also here we've taken the derivative now, so we can just plug in phi equals 90 degrees. So this becomes 1. This becomes 0. This becomes 1. So this is equal to omega dot r plus omega dot L plus omega L dot A3 hat. Plus, in this case, we have now negative omega crossed with omega r plus omega L. So this gives me omega squared r plus L. And because it's an A2 crossed an A3, that means it's A1 hat. So we have negative omega squared times r plus L. I think that is correct. Let me just check. Yeah, wait, yeah. I guess I could simplify this more. I just make this like omega dot times r plus L plus omega L dot A3 hat minus omega squared r plus L A1 hat. Okay, and now we've done that. Okay, honestly, this is going much quicker than I thought it was last time. I don't know what changed, but this then, right, our expression for A of P and E at phi equals 90 degrees is now just equal to, so we can I just like copy this? Oh, it's too much. Okay, well, maybe, okay, actually, you know what, it's fine. Then we do this one. Oh, I think it's breaking. Okay. Okay. Plus this. Okay, that looks kind of ugly, but we get the point. So this is a correct expression. However, we can simplify this further because what happens when phi equals 90 degrees? So when phi equals 90 degrees, I'm just going to draw this down here. So actually, no, I probably should not try to draw. Okay, when phi equals 90 degrees, Tom is like straight up like here. So what his frame then looks like, what the B frame will look like is this. So our A frame is, you know, always looking this way. I'm not going to draw the A3 hat just so we have a clean picture. But when phi is at 90 degrees, when Tom is over here, then B1 points in the same direction as A1. And then B2 hat points in the same direction as A2 hat. So what does that mean? That means we clutch and we can simplify our expression a lot. So I guess that's what they mean by nice expression. They want you to think about how the frames can look really clean. So let's do this. So we know that we can also say that f equals 90 degrees. We know that b1 equals a1. b2 equals a2. And we already know that b3 equals a3. Even when it's not at 90 degrees, it's always equal to that, just based on how we defined our frames. So this becomes then, we can combine the b1 and a1 terms. So we get L double dot minus L phi dot squared minus omega squared r plus L a1 hat. And then the b2 hat, we can just say it's equal to 2L dot phi dot plus L phi double dot a2 hat. And then we can combine our b3, so we finish this one. And then we combine our b3 hat and a3 hat terms. So this gives us phi dot r plus L plus 2 omega L dot a3 hat. Okay, and this is our expression for the acceleration of p at e at phi equals 90 degrees. Whew, okay. This is the correct expression, but let me just check in case I am sorely wrong. Phi dot squared. Yep, this is correct. Okay, yay. Okay, that was a hefty problem, but hopefully you can see the process. I think really once you figure out what the drawing is looking like, it makes everything a lot easier. The tricky part is really just this vector projection. But we basically established our frames, found these expressions, which made our lives a bit easier later on. And I think it's just a matter of keeping track of, or noticing certain mathematical things, like for example, this part, that will help your answer become a lot cleaner later on. And just as a reminder, you should never take the derivative you should never plug in the values at a point and then take the derivative. You always take the derivative of the general expression first and then plug in the values at that point. And then you just BKE the crap out of it and you get this expression. Okay, next problem. So in problem 4, wait, I actually wonder if, no, I don't think so. Okay, anyways, I thought this was a special expression. Anyways. Maybe it is, I'm just wrong, but okay, anyways. So in problem 4, we have the cart is negotiating a turn of radius r equals 35 inches. At constant speed, v equals 15 miles per hour. The boom is being raised relative to the cart at a constant rate, omega, equals 5,000 radians per hour. So that's lovely. They give us these things, and then it says, find a nice expression for the angular velocity of omega of the boom with respect to the fixed frame, f, and then the angular acceleration. Wait, what? Okay, I think this is a typo. I think this is supposed to be an f. Anyways, find nice expressions for the angular velocity and the angular acceleration of the beam where f is fixed in the ground. I think I did do this problem in one of the other videos. This might have been an exam 2 problem, but I'll just do it again here, and maybe I can explain it better, actually. Okay, so first of all, as we normally do, we create a reference frame for each of the complex rotations we have. So first of all, this cart G is rotating around this turn, and then on that cart, we have a rotation of this boom at angular velocity omega. So we clearly have two complex rotations that depend on each other, right? The boom is rotating relative to the cart, which is rotating relative to the ground. And F is fixed in the ground. So let's first draw F. I'm going to draw the F frame in terms of the view from above also. So this can be the F1 hat direction, F2 hat, F3 hat comes out of the page. And then the first thing I'm going to do is I'm going to delete these two just for cleanliness. So the first frame I'm going to create is the frame for the cart. So I'm going to draw a frame called the A frame, where the A1 hat vector points towards the cart and is rotating with the cart. And the A2 hat vector is, of course, orthogonal to it, so perpendicular. And the A3 hat vector comes out of the page in the view from above. Then I want to create a frame for the boom, which is fixed in the boom. So there's a vector that's along the boom this way. So this is the B1 hat vector. This is the B2 hat vector. And then B3 hat comes out of the page. And this is from the view from behind. So the angular velocity of the boom with respect to the fixed frame in the ground is going to be equal to the angular velocity first of the boom relative to the cart, which is rotating. So of the angular velocity of the B frame with respect to the A frame, plus the angular velocity then of the cart relative to the fixed frame in the ground. Right? The stuff is rotating relative to each other. So this is then equal to, if we do the right hand rule, we curl our fingers in the direction of the rotation. So for the cart, so let's do the angular velocity. Let's do this one first. So the angular velocity of the B frame with respect to the A frame is going to be omega, right? It's rotating at omega relative to the cart, right? This is what it says in the problem. So this is how we know it's not relative to the ground. So this is going to be equal to curling our right hand fingers in the direction of omega. Our thumb should be pointing out of the page, which is in the direction of B3 hat. So this means that this is equal to omega B3 hat. Now the angular velocity of the A frame with respect to the F frame, so this cart is rotating around this way, right? So from physics, we know that the angular velocity is then equal to the tangential velocity divided by the radius of the turn. So this is going to be equal to V over R from physics. So we know that it's also rotating this way, right? Going this way around the bend. So we can curl our fingers and we notice that our thumb is again pointing out of the page, our right thumb. So that's in the direction of A3 hat. So that's going to be V over R A3 hat. Yeah, so that's our expression for the angular velocity of B and F. B with respect to the F frame. Okay, and then now we want to find the angular acceleration. Oh wait, we should put in numbers. I forgot this one has numbers. Okay, so how do we do this? Sorry, I kind of don't know how to work with numbers anymore. Okay, so omega is equal to 5,000 radians per hour. It's lovely. B3 hat plus V over R. So V is 15 miles per hour. And then R is 35 inches. Oh, this is going to suck. Okay. A3 hat. Okay, let's see if I can remember how to do dimensional analysis. So 15 miles per hour. Okay, it does say in SI units, so we should probably do... Oh yeah, so this should be... Oh, okay, so radians per second. So this... Okay. Let's do... Okay. Wow, I cannot handle numbers. Okay. 15 miles per hour times 1 over 35 inches. So first we need to convert the miles into inches. So 1 mile is equal to... What is this? Oh, okay, wait, what? Bruh, okay. Let's do this then, because they gave us these coordinates. So let's do 15 mph times, so 1 mile per hour is equal to 1.6 kilometers per hour. So this cancels this. And then, okay, so, bro, my brain is breaking right now. Okay, 1 kilometer is 1,000 meters. 1 meter is 100 centimeters. And then, okay. And then we also have this, like, we have this 1 over 35 inches. And then we get this one, which is 1 inch is 2.54 centimeters. So 2.54 centimeters equals 1 inch. So this allows us to cancel this, cancel this, cancel this, cancel this. So this gives us 15 times 1.6 times 1, 2, 3. So I guess this is a 26996.625. Wait, what? Oh yeah, so we have eliminated the units of distance. So we have, then what's left is radians per hour. Okay, and let's convert now. 1 hour is 3600 seconds. So this becomes 7.499 radians per second. Okay, and then we are happy with that. And then this becomes, we just do the same conversion. So 5,000 radians per hour times 1 hour is 3600 seconds. And this is equal to 1.389 radians per second. Okay, so our angular velocity of the boom with respect to the F frame is 7.499 A3 hat plus 1.389 B3 hat. And this is all in terms of radians per second. Wait, am I? Yeah, okay. And then another way you can express this, right? I think in the previous problem, we did a lot of those like, oh, look at these vectors and the way they point. So basically we can rewrite this B3 hat, which you see points out here. If we look at this view from the view from above, we can imagine that we're looking this way and a B3 hat points this way because of that. Right, because this is the view from behind, so if from the view from behind B3 hat points out of the page, then from the view from above it points this way. So I think if you maybe squint at it a bit, maybe you can see where it's coming from. What this means is that B3 hat is equal to negative A2 hat, because A2 hat points perpendicular to the direction to the cart, which is equal to the distance, well, not equal to the distance, it is in the same direction as the tangential velocity, which is pointing this way. So A2 hat and V point in the same direction. So this means that B3 hat, by pointing in the opposite direction of V, is in the negative A2 hat direction. So then I can just actually write this more simply as okay. I think that's all for part A, or I guess this first part. Okay, so now part B, which is find the angular acceleration of the boom with respect to F. This is a typo. So this is just BKE then, because we have to take the time derivative of the angular velocity of B with respect to F, which is equal to, so we said that B3 hat equals negative A2 hat, right? So this can be written as V over R A3 hat minus omega A2 hat. And again, this just makes our lives easier because when we take the BKE of that, so when we do the BKE of this, we have V dot over R. I think I guess you were supposed to assume that the radius of the turn is constant. I'm guessing it's a circular turn. Maybe it's not very worded very correctly, but this is a circular kind of depiction, so I would guess that the radius is constant. Although it really should mention it is in the problem. Because like who knows, your radius could be changing over time if you're like, for example, not that you're like in space, but like if you're a satellite and you're going around, notice that the radius of your turn is different. So in this case, I'm pretty sure what they really mean is like it's like a circular turn. So you would have constant radius r. And then it also says we have constant speed v. So this means that v over r is constant, so the time derivative is equal to 0. How do I write this cleanly? So this is equal to 0. And then we have minus omega dot a2 hat. And then omega dot is also going to be 0 because it says constant rate omega. So this is 0. So this is the time derivative with respect to the frame it's written in, but then we have to do the omega of a with respect to the f frame crossed with the original vector, which is just v over r, a3 hat minus omega a2 hat. And omega of a and f is what we found here, which is v over r, a3 hat crossed with v over r, a3 hat minus omega a2 hat. Because we found that above, right? Okay, and we do cross product. A3 cross A3 is 0. A3 cross A2 is negative A1 hat. So we have V over R times omega A1 hat. So that negative cancels with this negative, so we have a positive in the end. So our final expression for the angular velocity, or the angular acceleration of the boom with respect to the F frame is equal to this. And now we have to do our conversions, but we kind of already did that already. So we know that V over R is equal to this. So that's equal to 7.499 radians per second times omega, which is equal to this. This becomes this times 1.389 radians per second. And like I guess the radian squared doesn't mean anything, it's just the same result. I'm honestly not sure why. I feel like radians are kind of strange. But we get 7.499 times 1.389, 10.416 radians per second squared in the A1 hat direction. Yeah, I don't know. I guess like because radians are dimensionless, so if you just like square them, it's still dimensionless. So that's why you have a single radians and not a radian squared. But anyways, that is the final problem. It was pretty straightforward. It was just a bit of conversions and complex rotation stuff. So this, I'm not sure this will be an exam one nowadays, but I guess it's still useful to learn. So I think that's the exam. So yeah, good luck.